In their pursuit to comprehend the first stars and galaxies that illuminated the cosmos, astronomers find themselves still grappling with uncertainty. However, with each discovery, they edge closer to enlightenment. This remarkable undeniable truth emerges from the unprecedented findings of the James Webb Space Telescope, a 1 billion-year time machine now marking its inaugural year of observations. JWST, designed to unveil the faint infrared glow of the universe's earliest luminous objects, has exceeded expectations. Webb's vision extends back to the initial few hundred million years following the Big Bang, offering superior data on newborn galaxies compared to any previous facility. The abundance of galactic baby pictures has surpassed even the most optimistic projections, with dozens of candidate galaxies emerging, much to the surprise of researchers like Charlotte Mason, an astrophysicist at the University of Copenhagen. The unexpected maturity of these early galaxies has prompted intense scrutiny and speculation among scientists and observers alike. Could these anomalous large and bright early galaxies be mere illusions, perhaps stemming from flaws in the telescope's initial observations, or if genuine, could they be reconciled within standard cosmological models? Alternatively, do they hint at a universe far stranger and more complex than previously imagined, possibly challenging the foundations of the Big Bang theory itself? Join us today as we delve into how the James Webb Space Telescope has reshaped our understanding of the cosmos. But first, let's rewind to the birth of the universe. Following the Big Bang, as the universe cooled, electrons, protons, and neutrons combined into mostly neutral hydrogen atoms, marking a period known as the cosmic dark ages. Then a pivotal event occurred. Most of the universe's mass, composed of elusive dark matter, began exerting its influence, eventually leading to the formation of the first stars. These stellar beacons illuminated the cosmos during the epoch of reionization, sparking a cascade of events that shaped the evolution of galaxies within a vast cosmic web. Meanwhile, Edwin Hubble's groundbreaking discoveries in the 1920s revealed that the universe is expanding. Subsequent observations, including those from the Hubble Space Telescope, unveiled an even more astonishing truth: the universe's expansion is accelerating, driven by enigmatic dark energy symbolized by the Greek letter lambda. By integrating the properties of cold dark matter, regular matter, and radiation into Einstein's general theory of relativity, scientists have constructed the lambda cold dark matter model, which remarkably aligns with a myriad of observational data. One way to validate this framework is by scrutinizing the very distant galaxies, akin to peering back in time to the initial few hundred million years after the colossal explosion that set everything in motion. During this period, the cosmos was comparatively simpler, making it easier for astronomers to compare against theoretical predictions. The quest to glimpse the universe's earlier structures began with the Hubble telescope in 1995. Over 10 days, Hubble captured 342 exposures of what seemed like an empty patch of space in the Big Dipper. To astronomers' astonishment, this seemingly dark expanse revealed thousands of galaxies at various distances and stages of development, stretching back much further in time than anticipated. In 2016, astronomers made a groundbreaking discovery with Hubble, the most distant galaxy known at the time, dubbed GNZ11. This faint smudge dated to approximately 400 million years after the Big Bang, challenged conventional notions of early galaxy formation. However, it did not fundamentally undermine the CDM model, partly due to its diminutive size, comprising only 1% of the Milky Way's mass. Yet astronomers needed a more potent tool to discern whether GNZ11 was an anomaly or part of a broader cohort of enigmatic early galaxies. Enter the James Webb Space Telescope, renowned as the largest and most potent observatory ever launched from Earth. Positioned 1.5 million kilometers away from earthly interference and cooled to near absolute zero, JWST carries a massive segmented mirror and highly sensitive instruments designed to unveil never-before-seen details of cosmic dawn. JWST's initial discoveries have already surpassed expectations, offering glimpses of galaxies astonishingly close to the dawn of time and probing exoplanet atmospheres with unprecedented precision. As Webb's vision extends back to the universe's earliest epochs, it promises to yield unparalleled insights into newborn galaxies, potentially reshaping our understanding of cosmic evolution. The implications of JWST's early revelations are profound, potentially rewriting the opening chapters of cosmic history and shedding light on fundamental questions about our existence in the universe. As Mark McCorian, a senior advisor for space and exploration at the European Space Agency, aptly noted, these machines are designed not to affirm the status quo but to challenge it, paving the way for paradigm-shifting discoveries. A key method utilized by researchers to assess the distance of celestial objects is a variant of the Doppler effect. Analogous to determining the location of an ambulance based on the pitch of its siren, astronomers measure the redshift of galaxies where the magnitude of redshift indicates the object's distance from us. JWST's data has already led to intriguing findings such as the discovery of galaxies with redshift values ranging from 11 to 20, hinting at the possibility of an incomplete understanding of early galaxy formation within the CDM model. In summary, JWST's unprecedented capabilities have begun to unravel the mysteries of the early universe, challenging existing models and paving the way for a deeper understanding of cosmic evolution. Researchers delved into computer simulations of universes governed by the CDM model and made a startling revelation: the early bright galaxies observed by JWST were significantly more massive than those simulated to form concurrently. This dissonance sparked debates within the scientific community and garnered attention from various media outlets, with some claiming that JWST was challenging the foundations of cosmology. However, not all experts were swayed by these assertions. One inherent challenge lies in the ambiguity of CDM's predictions. While concepts like dark matter and dark energy are relatively straightforward, visible matter exhibits complex interactions and behaviors, especially in the tumultuous early years following the Big Bang. These chaotic times must be approximated in computer simulations, introducing uncertainties into the models. Another complication arises from the difficulty in accurately determining the distances of galaxies. In the months following the initial papers, the ages of some purported high redshift galaxies were reassessed due to updated telescope calibrations. For instance, Sears 1749 was found within a galaxy cluster whose light dates back 12.4 billion years, suggesting it might be a nearer object masquerading as a high redshift galaxy due to dust obscuration. Now, among others, highlighted the potential existence of new types of galaxies, confounding researchers. Sears 1749, regardless of its distance, represents a peculiar case, potentially defying conventional expectations with its low mass yet significant dust content. To obtain more definitive distance estimates, researchers anticipated leveraging JWST's most potent capability, spectroscopy. Unlike photometry, which measures brightness, spectroscopy analyzes the wavelengths of light, akin to conducting a DNA test to unravel an individual's ancestry. While initial observations relied on photometric measurements, combining spectroscopy with photometry for 4 galaxies revealed redshifts up to 13.2, indicating light emitted 13.2 billion years ago. The unveiling of these spectra sparked excitement among researchers, signaling a potential shift in our understanding of the early universe. Brant Robertson of the University of California, Santa Cruz suggested that these findings imply rapid evolution in the early universe, with galaxies evolving 10 times faster than today, akin to a hummingbird's accelerated heartbeat compared to larger creatures. However, questions lingered regarding whether these rapid changes were compatible with the CDM model. While JWST's images captivated astronomers and the public alike, researchers worked diligently behind the scenes to discern the true nature of the observed galaxies and refine the parameters of cosmological equations. Key among these parameters is the mass of early galaxies, crucial for assessing their growth over time and reconciling with CDM predictions. Determining a galaxy's mass from its brightness relies on assumptions grounded in our understanding of stars and galaxies. However, Megan Donahue, an astrophysicist at Michigan State University, cautions that this relationship is at best an educated guess. It hinges on assumptions regarding the initial mass function, IMF, which dictates the statistical range of masses in which stars typically form. The IMF assumption is crucial because while hot blue massive stars emit more light, the majority of a galaxy's mass resides in smaller, cooler red stars. Yet it's plausible that the IMF varied in the early universe. If so, the early galaxies observed by JWST might appear brighter than they actually are, potentially challenging our understanding of galaxy formation. Rachel Somerville, an astrophysicist at the Flatiron Institute, suggests that tweaks to the IMF and other factors could reconcile the ancient galaxies observed by JWST with the CDM model. She posits that perhaps gas in the early universe cooled and condensed more rapidly, leading to faster star formation. Another intriguing possibility is the role of black holes in the early cosmos. Glowing supermassive black holes observed at redshifts of 6 or 7 billion years after the Big Bang could explain the brightness of early galaxies, even if they aren't exceptionally massive. Confirmation that the CDM model can accommodate some of JWST's early galaxies came from simulations conducted by Benjamin Keller and his team at the University of Memphis. Their findings reported on the preprint server r14.org indicate that the simulated galaxies align with JWST observations, alleviating concerns about the compatibility of the observed galaxies with the prevailing cosmological model. Furthermore, JWST's discoveries hint at the existence of population 3 stars, the first generation of stars to ignite. These stars, unpolluted by metals from previous stellar generations, may have contributed to the reionization of the universe. The revelation of shockingly massive and old galaxies in the early universe, as observed by the James Webb Space Telescope, initially rattled astronomers' fundamental understanding of the cosmos. Dubbed universe breakers, these galaxies appeared to defy the expected size and mass for their age. Some speculated that these early galaxies might be much larger than anticipated, challenging the lambda cold dark matter CDM model, a key tenet of modern cosmology. However, as more data emerged and theories evolved, it became evident that these findings could be reconciled with our current understanding of galaxy formation. JWST's unprecedented infrared sensitivity allowed it to peer into the distant universe and uncover galaxies that formed less than 500 million years after the Big Bang. The early observations suggested that these galaxies were far more massive and luminous than previously thought possible, raising questions about how such galaxies could have formed so quickly. One of the earliest and most significant discoveries was a galaxy dubbed JWST 130, which existed just 320 million years after the Big Bang. Its rapid formation and large mass sparked intense debates in the astronomical community. Several explanations have been proposed to account for the presence of these massive galaxies in the early universe. Some scientists suggested that early star formation was much more efficient than previously believed, with stars forming at a faster rate and producing more luminous galaxies. Others hypothesized that the galaxies might contain significant amounts of dark matter, which could have helped accelerate their growth. Additionally, the presence of supermassive black holes at the centers of these galaxies could have contributed to their rapid accumulation of mass.